what this leads to, and this is just going to be a hand-waving description. It is something that takes a while longer, but comes out of the mathematics of waves. You don't need to come up with any extra quantum mechanical description. It just comes from a wave behavior. Because of this wave-particle duality, we cannot accurately know at the subatomic scale both position and momentum of a moving particle. So the uncertainty in x and the uncertainty in the momentum, mass times velocity, have to be greater than or equal to Planck's constant. You have h bar is Planck's constant divided by 2 pi, h bar over 2. Now this is a very small number, so these uncertainties can still be quite small. It's only when we're dealing with things at the length scale and the mass scale of atomic particles that it really matters. So what does it say? If the uncertainty is x in small, then the uncertainty in the momentum is large. So a large uncertainty is momentum means that h over uncertainty momentum, if delta v is large, then the uncertainty in the momentum is large, and therefore the uncertainty in the wavelength is small. We know we have localized the object, we know where it is. On the other hand, if the uncertainty in the momentum is small, then the uncertainty in x has to be large. So small uncertainty in velocity means that h over uncertainty momentum would give you a very large uncertain wavelength, so we don't know where it is. So that's how that relates. And again, this is a very rough explanation. It comes out of the math of waves, and when you look at wave packets, when you when you assume a particle is, that's localized in space is made out of not just one wave, but sums of waves together. If we had a couple days, we could get into it more. But this part of it is really, the Heisenberg uncertainty principle comes solely because of the wave nature of, so because of the Heisenberg principle, we do not know exactly the locations of particles with small momenta. It turns out, and this is a little more complicated, that we can know the probability of a particle being at x, y, and z. We know where the waves are more or less probable. We can see where the peaks are, we can see where the troughs are. The peaks correspond to more probable locations. Actually, the troughs do as well. It's when it's neither a peak or a trough, responds to not very much probability. So if you look at a classical trajectory, it looks like this. If you look at a quantum mechanical probability distribution, you get much more noise. And the more classical it is, the more it's approximately the same as the classical trajectory. You can show that the less trajectory is like classical, the less likely it is. So what we can get out of these is probabilities. We can't know exactly where particles are, but we can know where they're more likely and less likely, because they are essentially delocalized. In the same way a wave isn't in one place, it's in lots of places. A matter particle that has some wave nature is not just in one place, it's spread out over lots of places. Oh, yes, so that's the idea of the wave particle duality. So I'll end with a joke here. So Werner Heisenberg and Erwin Schrödinger are stopped for speeding, and the cop comes over and asks Heisenberg, okay, do you know how fast you were going? Heisenberg looks around, notices that he's exactly at a mile marker and says, I'm sorry, officer, I don't know. The officer's pretty ticked at this, and so he asks, all right, asks Schrödinger, so okay, what do you know what you have in the trunk of the car? Schrödinger says, I'm not really certain. The officer's very upset and says, fine, I'm going to open the trunk for myself. No, the cat might die. All right, so that's the quantum mechanics joke to lighten up the heavy discussion about quantum mechanics.